Welcome to Flynn Animations. Have you ever wondered how a tiny pill knows exactly where to go in your body, and why doesn't it just affect every organ equally? Today, we're diving into the biology of drugs, the science of the blood-brain barrier, and the elegant lock-and-key mechanism that makes it all possible. Hi, I'm Flynn. Today we'll look at some drugs, paracetamol and some others like cannabis and cocaine. Same principle, completely different molecular stories. When you swallow a pill, it first hits your stomach. Stomach acid breaks the pill down into individual molecules. Some pills have a special coating to survive the acid. Next, it comes to the small intestine. This is where absorption happens. The drug molecules cross the intestine wall into the bloodstream. The bloodstream carries everything, everywhere. The drug arrives at your brain, liver, kidneys, muscles, all at once. So yes, the drug is going everywhere, but just arriving doesn't mean doing anything. To have an effect, the drug needs to bind to a receptor. A receptor is a protein on, or inside, your cell. Only the right-shaped molecule activates the right receptor. This is called the lock-and-key model of receptor binding. The receptor has a specific binding pocket, a very particular shape. The drug floats toward the receptor, attracted by charge and shape. When it fits, click. The receptor changes shape. That shape change sends a signal inside the cell. That signal creates the effect. Pain gone, inflammation down. The reason drugs are selective is molecular shape. Your body has hundreds of different receptor types. Paracetamol fits the COX enzyme, not the sleep receptor. Wrong key, wrong lock, no drowsiness, no sedation. Drug developers spend years engineering exactly the right shape. Molecular architecture, billions of years of evolution, then humans improving it. Now, before cocaine and cannabis, meet the brain's best bouncer. Your brain is incredibly sensitive. It needs protecting. Blood vessels inside the brain are sealed by tightly packed cells. This is the blood-brain barrier, the most selective door in your body. Only small, fat-soluble molecules can slip through. Most antibiotics can't cross it, which is why brain infections are so hard to treat. Paracetamol barely crosses it, enough to quiet brain pain, not much else. Cannabis and cocaine? They cross easily. That's why they affect your mind so powerfully. Let's look at each one. Starting with paracetamol. Paracetamol, Tylenol, Panadol, Calpol. World's most used drug. Embarrassing truth is scientists still don't fully understand how it works. The leading theory is it blocks enzymes called COX. COX enzymes make molecules called prostaglandins. They amplify pain. Paracetamol blocks COX, fewer prostaglandins, quieter pain signal. It works mainly in the brain and spinal cord, not the whole body. Ibuprofen does the same thing, but hits COX everywhere, including your knee. The liver processes paracetamol into a toxic byproduct called NAPQI. At normal doses, your liver neutralizes it instantly. Overdose it. Liver failure. Cannabis? The molecule that gets you high is THC. THC crosses the blood-brain barrier easily. It's small and fat-soluble. Here's the surprising thing. Your brain already makes cannabis-like molecules. They're called endocannabinoids. The main one is anandamide. Anandamide binds to CB1 receptors in the brain. CB1 receptors regulate mood, memory, appetite, pain, time perception. THC is shaped almost identically to anandamide. Same lock, different key, but THC stays on the receptor much longer than anandamide. The signal gets turned way up. Time distorts, memory blurs, appetite spikes. This is why cannabis can genuinely help with chronic pain and nausea. It's not a placebo. It's a molecular impersonation of something your brain does. Cannabis, a molecule pretending to be you, but staying too long at the party. Now what about something like cocaine? Cocaine works completely differently. It's about dopamine. Dopamine is your brain's reward molecule. Pleasure, motivation, drive. Normally, a neuron fires and releases dopamine into the synapse. Dopamine crosses the gap, hits receptors, creates a reward feeling. Then the dopamine gets recycled. A transporter protein sucks it back in. This is the DAT transporter, the brain's dopamine recycling system. Normal cycle, release, bind, recycle, clean and controlled. Cocaine is shaped to fit the DAT transporter and block it completely, like jamming the recycling door open. Dopamine can't get back in, so dopamine floods the synapse. The reward signal is massively amplified. That's the high, an enormous artificial dopamine surge. But the brain adapts. It removes dopamine receptors to compensate. When cocaine wears off, dopamine returns, but now you have fewer receptors. That below normal state is the crash, the depression, the craving. Cocaine doesn't create pleasure, it hijacks your reward system and damages it. So where do side effects come from? No drug is perfectly selective. It partially fits other receptors too. Those unintended bindings create unintended effects. Side effects. Antihistamines block histamine receptors in your nose. That's the intended effect. But old antihistamines also hit acetylcholine receptors in the brain, causing drowsiness. Newer antihistamines are engineered to be too large to cross the blood-brain barrier. Same effect on the nose. Far fewer side effects. Every side effect in medicine is a drug finding a lock it wasn't designed for. The goal of modern pharmacology, make keys that only fit one lock. So, how do drugs know where to go? They don't. They go everywhere, but they only act where they find the right receptor. Paracetamol blocks COX enzymes in the brain and spine. Pain quieted. Cannabis impersonates your own anandamide and stays way too long. Cocaine jams your dopamine recycler, floods the synapse, then the crash. Same principle, lock and key, three completely different outcomes. And it all comes down to molecular shape, just the shape. Thanks for watching. Subscribe if you want more Flynn Animation science facts.